start examining the requirements for a physical process which can implement a quantum computer. And the first requirement is this. Instead of one bit in a classical computing system, we now need this notion of a qubit, a quantum bit, which can have an infinity of possible states instead of just two. You probably remember that the classical unit of information, one bit, can have only two states, which we denote as 0 and 1. Any physical entity which has two different states can encode one bit of information. And one bit of information is enough to describe the state of this entity. A switch, for example, has two different easy distinguishable states and can implement one bit for us. One switch has two different states, two switches, 4 different states, 3 switches, 8 different states, etc. If we need a system having 1024 different states, we need just 10 switches. And one bit corresponds to the state of the simplest possible classical computational system. Now, in mathematical model of quantum computing, the simplest quantum system is represented by one qubit instead of one bit. This qubit is a much more complicated thing. It is a unit vector in a two-dimensional Hilbert space. We are not going to discuss here what a Hilbert space is. The much simpler way is to think of a qubit as of a two-dimensional circle. We have two special points or special values on this circle, which we call 0 and 1. And they correspond to the possible values of a classical bit. So the qubit can represent for us a classical bit. It has two corresponding states. But it can have much more other states for which we don't have analogs in classical bit. Any point on the circle can be the qubit value. And in the basic quantum algorithms, we are particularly interested in these two states, which we denote plus and minus. The state plus, for example, represents for us a superposition of 1 and 0 states. We'll talk about this superposition later. Some of you who are already familiar with the mathematical model may object that this simplification is not exactly correct. Any point on this circle can be represented with this formula. Thus, we need only one real parameter, theta, the angle to define the state here on this circle. But the real qubit is defined by two real parameters, or even by two complex numbers. This formula, for example, defines a perfectly valid qubit, which does not correspond to any point on this circle. We will see later on the week 2 that geometrically this formula defines the state which rotates counterclockwise, passing all the points on this circle. But that's okay for me. There exist quantum algorithms that show exponential speedup over classical computers which never employ these complex numbers and states defined by them. So if we are able to design this type of qubit without complex numbers, we would be able to run those algorithms, which is very good for us. Now, many of you already noticed that the qubit seems to be a much more powerful thing than classical bit is. Classical bit can store one of two values, while quantum bit can store one of infinite number of values. This is what usually mentioned when people try to explain the power of quantum computing. Quantum computer works with these wonderful things, qubits, which can store so much information, infinitely more than normal bits, etc. Well, yes, we really need this type of information in mathematical model, and it really seems more capacious. But wait, can't we make such things on a classical physical process? I mean, quantum computers are believed to be extremely powerful. They can break ciphers, etc. And the only obstacle is to implement this circle instead of a normal bit? Of course not. We can easily implement this thing. Consider a pendulum, which can swing at any direction. The direction of its swinging can be any of these directions. Each of them we can mark as a point on the unitary circle. It can swing here, and we will denote this as 0. And it can swing here. We can denote this as 1. And any other state it can also do. And this pendulum can not only swing, representing these simple states, it can rotate, like this, representing the complex number states for us. And on the first glance, it looks like a very good device for representing a qubit. So why don't we implement our quantum computers on numerous tiny swinging pendulums? That would be a very lovely thing, this computer. The thousands of pendulums swinging and rotating in different directions. Consumers would surely pay for this. But it appears that this infinity of states is not enough. It is just not the only source of the quantum computer magic. We have other demands which mathematical model of quantum computing have placed for us. The next in the row is true randomness. Let's see what's it about in the next episode.